why this can be interesting, maybe not only for the standard supergravities, which we know already in the traditional language, but why this can be also interesting maybe to study exotic gravity, exotic supergravity. And by that, I mean, I'll talk about that in more detail. Exotic gravity refers to particular 6-dimensional theories in which the spin 2 sector is not carried by a graviton, like a symmetric tensor, but is carried by a mixed symmetry tensor field. Okay, so technically it's still spin 2, but it's for me that's almost like higher spin. So this one doesn't work. Okay. So just a few words on the context. All this goes back to work from the beginning of supergravity in the 80s, end of the 70s. And all that goes back to the observation, which was made at the time, that whenever you construct maximal supergravity theories, and the way you typically construct maximal supergravity is by reducing higher dimensional supergravities on tori, what you end up with are maximal supergravities in lower dimensions, and those come with very big symmetry groups. And those are the exceptional groups, E6, E7, E8, and so on. So for example, if you take 11-dimensional supergravity and you reduce it on a 7 torus down to 4 dimensions, you will get the 4-dimensional maximal supergravity, and it comes with a global symmetry group E7, and nothing of that was present in 11 dimensions. So that's really like a feature of which comes after reduction. Similarly, if you take type 2b supergravity in 10 dimensions, you reduce on a 5 torus, say you come to 5-dimensional supergravity. That's still a maximally supersymmetric theory. It comes with a global symmetry group, which is E6. Again, nothing of that was present in type 2b supergravity. And the way these groups appear is typically only after you properly organize the fields. You sort of do field redefinitions, you dualize a part of your fields, and only once you've found the good objects, you can make this symmetry manifest. Okay, and so the idea of exceptional field theory is, or the underlying theme is, to see to which extent one can make these structures already visible in the higher dimensional theories. So to which extent one can see something of E7 or some remnant of E6 already before actually doing the reduction. Okay, so that's the philosophy. No, okay, sorry. So E6 is just the Lie algebra E6, 78-dimensional. E7 would just be the Lie algebra E7. What I refer to in parentheses is the real form. Okay. In particular, the groups which show up here is always the split form, the split real form of those algebras, the most non-compact form which you can find. Okay, so those are, it's not the compact symmetry groups, they have a compact and a non-compact part. Okay, and that typically you label by those numbers in the brackets. Okay, so there's a number of concepts which come together in this, from double field theory, generalized geometry, exceptional geometry, gauged supergravity, which go together in this construction of exceptional field theory. And so that's a small, short outline. So I'll discuss this framework of exceptional field theory, construct one of those theories based on ingredients coming from exceptional geometry and the tensor hierarchy, and then construct invariant action functionals in this framework, which then will turn out to be like alternative equivalent action functionals of 11-dimensional supergravity and of type 2b supergravity. So that's mostly work with Olaf Holm. And then among the applications, as I mentioned, I will discuss how this may also be a good framework for those 6-dimensional exotic supergravities. And that's work with Stefan Hohenegger in Lyon, our student Yannick Bertrand, and also Olaf Holm. Okay. Okay. So the example I choose is exceptional field theory for the group E6. In principle, that's a construction which you should do case by case for the different groups. Each one comes with a few technical subtleties, but morally, it's always the same construction. So I choose E6 because it's kind of the one which has least of those technical subtleties, and yet all the structure of an exceptional field theory. Okay, so remember, E6 is the group which I find in 5 dimensions. So which I find, for example, if I take 11-dimensional supergravity and I compactify it on a 6 torus. And so this would really be just a classic Kaluza-Klein reduction. I start from 11-dimensional supergravity. I split my coordinates, 11 coordinates, into this is 5 x's and the 6 coordinates y on the torus. And so that means all the fields in 11-dimensional supergravity I decompose a Kaluza-Klein style. So this would be the P form, the 3 form, which features in 11-dimensional supergravity. And depending on how I distribute the legs of that 3 form in the 5-dimensional theory, this will look like a bunch of scalar fields. This looks like a bunch of vector fields. This is a bunch of 2 forms, and there will be a single 3 form after reduction to 5 dimensions. Okay, then you do the same for the metric, standard Kaluza-Klein style. You find a Kaluza-Klein vector in the metric, a block of scalars which contribute to the scalar sector, and so on. Then comes the work, because if you just look at these objects, there's nothing which looks like E6 big enough to fill some E6 representation. So you have to dualize, redefine fields, and so on. You're in 5 dimensions after this reduction. So these 2 forms in 5 dimensions, you can dualize them into yet more vector fields. A 3 form in 5 dimensions, you can dualize it into a scalar field, and so on. And once you do all that, I don't go to the details. That's the result which was obtained already by Kremer in the 80s, which is like a standard result in supergravity. That's the 5-dimensional bosonic Lagrangian, which you find after doing all this work. And as a 5-dimensional theory, it looks extremely simple. It has just 4 terms, and every one of these terms has a very standard form. So that is just the Einstein-Hilbert term in 5 dimensions, standard general relativity. M is a matrix of size 27 by 27, but which only carries 42 independent components because it parameterizes the coset space E6 over USP8. Okay, so 27 is not by accident. 27 is the fundamental representation of E6. So you can think of this as like a group matrix on E6, but it's symmetric and positive. So in fact, it parameterizes this coset space. USP8 is precisely the compact part in this non-compact Lie algebra. Okay. M with indices up is the inverse matrix. And so that is a kinetic term for scalar fields in 5 dimensions. And since M has a group structure, in fact, what this describes is a coset space sigma model in 5 dimensions. And it's a coset space sigma model where the target space is precisely this coset space. Because it's symmetric, you can think of this, it's symmetric in the indices. Okay, so you can think of this as an element of E6 multiplied by its transposed. And then the gauge freedom which you have, right multiplication by compact elements corresponds to dividing out USP8. It's symmetric. It's a symmetry which implements the coset space. Okay. Very good. So 42 components sit in here. That's the coset space sigma model. There are 27 vector fields. Again, they come from different high dimensional fields. Those 27 vector fields, I will label them with this, again, with this capital index M. That is a fundamental representation of E6. And they come, as you see, with a standard Maxwell term in the theory. However, M and N must be contracted, and that happens by means of this scalar dependent matrix. Okay, if I would contract it with a delta Mn is not an E6 invariant tensor. So the way to have an E6 invariant Lagrangian goes with a scalar dependent coupling. But that's very typical in supergravity. Say again. F is, okay, I didn't spell it out. It's just the abelian field strength of this guy. Abelian. So it's like, here I have a gauge group, which is just U1 to the 27. Yes, but think of this as decomposed into like the metric. Think of this decomposed in a vielbein. Okay, vielbein times its transposed times the transpose implements symmetry, but the vielbein lives in E6. So the vielbein only is a 27 by 27. It's a group matrix. The vielbein is a group matrix of E6. It's a 27 by 27 matrix. But since it's a group element of E6, it only carries 78 parameters. And now yes, it's a group. It's a group matrix. So it's not an arbitrary 27 by 27 matrix. It's an element of the group. And as such, it only carries as many parameters as the dimension of the group. The vielbein lives on the group. Vielbein in that sense. So imagine of this guy as being written as a product of two matrices. And then contracted with a tensor. That is an E6 element, an arbitrary E6 element. So this has only 78 parameters. Okay, I square it, it still has only 78 parameters, but I contract them. This is a tensor. E6 doesn't have such a tensor. This is a USP8 invariant tensor. And so USP8 goes, it's absolutely, that's what I'm saying. Yes, yes, yes. Okay. Okay. So we had the 27 vectors. Again, we are in 5 dimensions. In principle, I could also dualize them into 2 forms. B, but I will not do so here, but that will become important later. In 5 dimensions, vectors and 2 forms can be dualized into each other. And then the last term is a topological term. So we're in 5 dimensions. There's a topological possible coupling F, wedge A, and that's precisely what comes from 11 dimensions. And now, in order to contract these 3 guys, I need a constant tensor, of course, in front, not a scalar-dependent one. But it turns out the group E6 precisely has a totally symmetric invariant tensor in its fundamental representation, the D symbol, the totally symmetric D symbol. And that shows up here as the coupling of that topological term. Okay, so it's precisely what is allowed for group theory and for the space-time dimension. So it's in some sense the most canonical thing you can write down. And that's all. That's the full theory. That's the bosonic. I will not talk about fermions in this talk. So that's the full bosonic sector in 5 dimensions. Einstein-Hilbert, sigma model, Maxwell term, and a topological term. And after you've done all this work putting together the objects, well, this Lagrangian has a global E6 symmetry, which is now manifest because all these objects will just rotate under E6. E6 just acts on its fundamental representation. It will just conjugate this matrix and so on. Yes. Right. In some sense, okay. In some sense, it's a mystery. You can think of it like that. A part of E6 is just simple geometric and related to the torus. And that is because I come from 11 dimensions. If I reduce on a torus, the symmetry which I expect to see is a GL6 symmetry, which is basically a transformation of the torus which survives the reduction. Okay, so inside of E6, there's a GL6 which is kind of geometric. And GL6 is already a maximal rank, it's already a maximal subgroup in here. So that one we understand. Together with that, there are a few symmetries, nilpotent symmetries, which are also obvious. Which basically come from what used to be tensor gauge transformations in the high dimensions. Okay, and that is like, okay, now I should do the counting, but I will not. Again, if I just give a sketch, you can, I mean, it's a bit sketchy, but think of it like that. So there's a GL6, which is kind of manifest and is there for geometric reasons. And then there's a bunch of nilpotent translations which come from high-dimensional tensor, the surviving tensor gauge symmetries. Those are there, but they're not terribly interesting. What makes all this interesting, and that's kind of the miracle of these hidden symmetries, is it's okay. There's supposed to be an algebra here. GL6 generators. I have an algebra made of generators Ni, nilpotent generators, and some grading which I put on this thing, and then the sort of miracle which comes in, which is the one we're trying to make to understand better, is that in fact all this will join into the algebra E6 after. Okay, I don't distinguish between algebra and groups. I mean, I'm just talking about algebras, of course, because they are compensated by what people call the hidden symmetries down here. So those ones are the miraculous ones. Okay, but there are just as many as those translations, such that the whole thing now becomes a semi-simple Lie algebra, which is E6. Okay, so there's sort of this upper triangular part, which is kind of geometric and easy, and should be there. And there's this part which is kind of the miracle. And I is generators. It's a decomposition of E6 into a GL6 subgroup and other generators. It comes from what used to be tensor gauge symmetries which survive the translation, which survive the reduction. Basically, it's like tensor gauge symmetries which are linear in the torus coordinates. Yes. Why they're important? Well, you could just say they're just there. What you see is if I reduce 11-dimensional supergravity on T6, some of what used to be local symmetries in 11 dimensions, some global subgroup of that will survive as a symmetry of the 5-dimensional theory. What property? It's every tensor gauge symmetry leaves some remnant in 5 dimensions. More specifically, well, it's those which you can think of as linear in the torus coordinates. Okay, because what we're doing here is we're doing dimensional reductions. Basically, we're saying that all fields, well, we simply drop sort of the internal coordinate dependence. Okay, so what I have in my higher dimensions is, for example, gauge transformations or diffeomorphisms. Let's take a gauge transformation lambda, which a priori also depends on x and y. Okay, let's say for my 3-form, I would have a 2-form gauge parameter. But of course, if I put here arbitrary y dependence, that will give us a transformation which is not compatible with my reduction. Okay, if I totally drop the y dependence, well, that will translate into gauge symmetry down in 5 dimensions. So the extra bit comes when I have a certain coordinate dependence, but a light one, a linear one. For example, think of lambda mu being, say, some constant matrix. Okay, let's go for some particular sector. So, for example, think of a constant matrix times linear in the torus coordinates. Then you can show the effect of this gauge transformation. In fact, the y will always drop out, and it will translate into global symmetry of what I have downstairs. So it's like a subsector of the local symmetries which go into something global downstairs. Right, but they are not. They are not because, okay, okay, unless in some really bigger framework, maybe, a priori they are not, because if you set up this framework for an arbitrary tensor coupling, say, in high dimensions, the algebra structure of what you obtain by such transformations will always be like a trivial, like a nilpotent algebra. Okay. Whereas here, the interesting part is, of course, that this commuting with that goes into GL6. And so you would really need some tensor, which is really not of tensor type upstairs to make to have these commute into something non-trivial. Right, but it would really have to be some kind of very exotic tensor, more exotic than what I, more exotic than what I. Yes. Yes. No, all this, I mean, down in 5 dimensions, all this is global. Everything is global, but it comes from local symmetries up in 11. So for example, the GL6 comes from diffeomorphisms. Is those diffeomorphisms in 11 dimensions, again, which are linear in those coordinates which survive the reduction. And this bit comes from, is the analogous thing, but from the tensor gauge transformations, and the new one, what people call the hidden symmetries and stuff. Okay. But as for the moment, this is, well, at the time, or it still is kind of a miracle why this is there. In some sense, I mean, one sort of hand-waving argument why this might be expected to be there is supersymmetry. Because in the end, these theories, they are defined by the fact that there's supersymmetry. Now, in 5 dimensions, the R symmetry, which you need to realize supersymmetry, is a USP8, a compact USP8. So in some sense, you would think that your fields should be such that you can easily realize a USP8 symmetry on that. And USP8 would not fit in this upper triangular piece. USP8 only fits once I also add the complement. But that's just giving you some hint why there should be why you might expect an enhancement. Okay. So that's the result. As we have put it now, E6 down in 5 dimensions becomes an honest symmetry. Nothing is now mysterious about that, and it rotates just all the fields. They all are in linear representations. All the scalar fields would be in a non-linear representation of that symmetry. Okay, but you have to do some work to get there. And the idea of exceptional field theory is you try to do exactly the same. So you do the same Kaluza-Klein reorganizing of fields. You do that same kind of regrouping of fields into a 27 component objects, into a big matrix, and so on. The only difference is throughout you keep the dependence on the internal coordinates. So you don't throw away the y dependence. And that means you still do this sort of block decomposition, dualization, regrouping. It becomes a little more complicated because now everything depends also on y. Okay, but if you do it properly, you can go through and you come to an action which looks very much the same if you give it in the right indices, if you identify the right objects. You see, I put it in a form which is really suggestive. Every term is the same, except for all the letters now became curly, which is a sign that now all these are subject to some infinite dimensional gauge structure. So what do I mean by that? Well, first of all, remember all these fields here now depend on the 5-dimensional space-time, but also still all depend on my internal space. Okay, I'll come to that. Yeah, exactly. That's the sort of all the features of the internal dimension are hidden in those covariant derivatives, in the fact that this is now not Maxwell, but a Young-Mills type of field strength, and in the fact that this has blown up into some non-abelian topological term, and there's some extra couplings here. Okay, so what are these covariant derivatives? Well, remember, this is still 11-dimensional supergravity. It just looks different. Okay. From that 5-dimensional point of view, we have now the full algebra of diffeomorphisms on that internal space, which we have not thrown away. Yes. That's the point. It's mu nu. This is like a 5-dimensional kinetic term. The action really looks like a 5-dimensional field theory, except for all the fields depend on 11 coordinates. Okay. No, I have to integrate this explicitly over my full space if I want to write down an action. Here, I hide them in the last term. And of course, I mean, here is all I cannot put elsewhere. But of course, there's a lot of, you will see, internal derivatives. A lot of them are hidden in the connection piece here and also in the Young-Mills extension of that field strength. Okay, but we still organize fields by sort of their 5-dimensional nature. Yeah, but it will be the square root of the determinant of that metric in front. Only the G-mean in front. And that is because typically if you do the dimensional reduction, you also will have to rescale your fields and all that. So all that will be taken care of. I will tell you in a moment. We have first we have to worry about those. I haven't actually defined much for the moment. I have just put letters here, and we have to understand those. Yes. 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 It is. It is indeed. But in some sense, it's you can. It's not really a surprise because I mean. That's precisely because if you do a reduction on a torus, and you do it naively, you just take your upper left block as the lower dimensional space-time, you know that you end up with a gravitational theory, but not in the Einstein frame. And you have to do a viral rescaling of the lower dimensional metric to come back to the Einstein frame downstairs. And that viral rescaling makes that in the end, there's only the determinant of the 5-dimensional metric in front. And since we have done exactly the same procedure, the same happens here, so there's no additional scale factor or anything. For the moment, nothing. For the moment, nothing. Okay, I just write out a formal. I just write out. I mean, this is. I'm not talking about integrating for the moment. This is just the Lagrangian. So I'm just talking about. I will just observe derivatives along those internal directions. Yes. Okay, so let's say what I'm doing here is local for the moment. Let's not think about global obstructions. Okay, yeah, okay. Let me come to that. Exactly. That was. I think that was my point. The starting point. What else I was starting to say. So, a remnant of what I see in this formulation should, of course, be the diffeomorphisms on the internal space. Okay. But so with a diffeomorphism parameter, which is like a vector on that internal space. But from that 5-dimensional point of view, this will look like a gauge transformation. Okay, like a bunch of gauge transformations. And those symmetries, which are the diffeomorphisms on the internal space, from the 5-dimensional point of view, that looks like an infinite dimensional gauge algebra. And that infinite dimensional gauge algebra is the diffeomorphisms on the internal space. Okay, that's not. That's just one way of thinking about Kaluza-Klein theory. Or doing Kaluza-Klein, keeping all the Kaluza-Klein towers means nothing else but organizing everything into a representation of the diffeomorphism algebra of that internal space. Okay, so let's make that a little more explicit. That is a non-abelian gauge structure. So in fact, okay, I said we have diffeomorphisms on that internal space, but we also have matter, so we have the P form, so that there will be also the remnant of the tensor, again of the tensor gauge transformations on the internal space. And turns out the nicest way to phrase all this is again to recombine all of that, to recombine internal diffeomorphisms with internal tensor gauge transformations, and see all that from the 5-dimensional point of view as some like infinite dimensional gauge algebra. It's made up from all what used to be local transformations, but now restricted just to the internal space. So before we go here, let's go. So we would combine all those gauge parameters into a single 27-component object, which is made of 6 components, which corresponds to the gauge parameter of internal diffeomorphisms. We're reducing on a 6-dimensional, or we have done a split with a 6-dimensional internal space. So internal diffeomorphisms correspond to 6 components of such a gauge parameter. There was a 3 form up in 11 dimensions. Its gauge parameter is a 2 form. So there would also be those gauge parameters with both legs on the torus, which are internal 3-form gauge transformations. Okay, so that would be 15. The 3 form in 11 dimensions, you could dualize it into a 6 form, and that also comes with its gauge transformations, and that would have like a 5 form structure. So another 6 components corresponding to internal 6 form gauge parameters. Okay, so all these should show up as gauge symmetries of my 5-dimensional theory. And by gauge symmetry, I mean they should depend on X, so they should be local in my 5-dimensional space, and there should be like honest gauge symmetries in 5 dimensions. But of course, they also depend on Y. So in that sense, they span an infinite dimensional algebra from the 5-dimensional point of view. Okay, it's just a rethinking of local symmetries into an infinite dimensional global gauge symmetry. Yes, that's right. Okay, but see, when I build up these E6 objects, I did have to do some dualization. So, for example, the 2 forms, which I found by naive reduction, I had to dualize them into vectors. And those vectors now will come with their own gauge transformation, which I have to accommodate somewhere. And the gauge transformation of those vectors will sit in here. Very good. I don't, because I don't see the 2 forms here. In some sense, this is just analogous to the fact that when I did the thing in the very beginning, I was dualizing all my 2 forms into vectors. Okay, so and I come up with 27 vectors, and by that I have not added any degree of freedom. There are 27 vectors because I have eliminated all the 2 forms. And what this is the gauge parameter of those 27 vectors. Okay, so the ones you have in mind, which I have, indeed, I have added some here, but I have not, I have eliminated some of those which used to be gauge transformation of 2 forms. Okay, so in the end, the counting works out. In some sense, I have 27 vectors, I should have 27 gauge parameters. So the counting is still okay. Okay. So that's the structure, that's the gauge parameter which has to act. And the way it acts is very neat. It acts by what people call generalized diffeomorphisms. So this is a gauge parameter. It acts on, say, another 27 component object, such as, for example, well, if I know how it acts on a vector, I know how it acts on tensors. So if I know this action, I can also have it act on this matrix M, and so on. And you see this action looks very much like a diffeomorphism. Now on this formal 27-dimensional space, well, because we have a 27-dimensional sort of generalized diffeomorphism parameter. Okay, if it were not for these brackets here, that would be the action of a diffeomorphism. Okay, but the action of a diffeomorphism cannot really be the right answer. Why not? Because we need something which should, for example, act on group matrices. And if I act with a diffeomorphism on a group matrix, it will spoil the group property. Okay, in GR there is no subgroup of metrics which are left invariant by the action of diffeomorphisms. Also, remember, for example, in this topological term, there is the D symbol of E6 showing up, which should remain constant under all this. So I need that the action of such a diffeomorphism on this cubic fully symmetric tensor is 0. Again, in GR with standard diffeomorphism, I don't have constant tensors except for the Kronecker delta. Okay, so that is why this cannot be a standard diffeomorphism, but instead, what turns out to be the right answer is the following. This is just the translation term of a diffeomorphism, but instead of this second term of a diffeomorphism, kappa is a number, it's 6. Sorry, yeah, it's a bad notation. Kappa is just a number. So what I do here is I consider this gradient of the gauge parameter, I consider that as a matrix, and that matrix I project it down to the algebra of E6. such that this second term, in principle, is nothing but an E6 rotation of my vector, and as such preserves the group structure E6. Okay, yeah, I come to that in a second. To the internal coordinates. Now you can say we don't have 27 internal coordinates, which is perfectly correct. I'll say that, and I'll specify that on the next slide. Inside of these 27 coordinates sit our 6 internal coordinates. Okay, take it for a moment just as an. So if I write down an action like that, this action by construction is compatible with the E6 group structure, so that can preserve group property of M and also the tensor property, the invariance property of the D symbol. Okay, so that turns out to be.
May I ask a question?
Yes.
My question is it fair to say that these generalized diffeomorphisms is some subgroup or subalgebra of 11-dimensional diffeomorphisms that leave invariant some structure associated with E7?
Is that some, you're saying, is that some subgroup of the 11-dimensional?
Well, it's a combination of, it looks like it is a combination of diffeomorphisms there and there.
Well, of course, I mean, of course, it must be more than the 11-dimensional diffeomorphisms, because it also carries all these remnants of the tensor gauge transformations.
Okay, yeah.
So it goes beyond that. Okay, let me come to Thomas' question then. So to write this action and to write it in a form which looks kind of E6 covariant, we have introduced as many derivatives as we had like diffeomorphism parameters. But of course, we know we don't have 27-dimensional internal space. So in fact, what we have done here is we have embedded those 6 coordinates, which we know are present, our 6-dimensional internal space. We have embedded that into like a formal derivative operator, a formal gradient in that 27-dimensional representation. And to encode the fact that we have not added any extra dimensions, which is not what we don't want to describe a yet high-dimensional theory, we still want to describe 11-dimensional supergravity, these derivative operators have to satisfy the following constraint. And that is kind of always subject of many discussions. There are many approaches to this. I'll take it very pragmatic. So whenever we hit 2 such derivatives by the D symbol of E6, the constant D symbol of E6, the answer should be 0. And what I mean by that explicitly is the following. These 2 derivative operators can either act on the same field or act on different fields. And whenever that happens, and they happen to be constructed with a totally symmetric D symbol, the result should be 0. Not to me. At the moment, I don't, well, in the sense that I'm writing down a 2 derivative action. But I'm not assuming, same, it's a 2 derivative action also with respect to internal coordinates. I don't do a Taylor expansion or anything. It's full coordinate dependence. But of course, in the action, it's not a high derivative action, so I only see a. Say again? Yes. So far, I haven't specified that. So I haven't specified that. I should specify that the moment I want to study particular solutions and so on. But at the moment, it's just writing an action. Right, but again, at the moment, I'm just looking at it locally, say on a given card. Okay, I'm not yet thinking about global obstructions. Okay, yes. This year? Yes. Oh, sorry, yeah, this is 27. The big capital M index is 27, and that is just 6. It is. That's the point. It is. It is. You see, I mean, we know 11-dimensional supergravity doesn't have an E6 symmetry, right? So why is it, good point, why is it broken in this form? It's precisely, it's hidden sort of in this embedding. It's because these are not all sort of derivatives on the same footing. They have to satisfy this constraint. And this constraint, it looks pretty strong, right? I mean, a condition like that is really not something I mean, it looks like it may not have any solution, but it does. It has the solution to restrict my 27 derivatives only to derivatives along 6 directions. If you do that, then these equations are satisfied, whatever f and g are. If f and g only depend on those 6 coordinates, then these conditions are satisfied. Okay, so you can think of that, and yet you could say, I mean, this constraint looks covariant. It looks E6 covariant. In some sense, it's a covariant formulation in the sense that this Lagrangian looks covariant. The constraint looks covariant, but the moment I solve it, well, I have to pick out 6 among the 27, and that moment I break E6. Okay, and so that's what happens. I break E6 down to GL6. Remember, that was our geometric subgroup. 27 breaks into, as we had, 6 and 15 and 6. And out of these 27, we only keep the 6 first derivatives, and that solves this constraint. They close precisely if you impose this condition. So if you compute the abstract algebra and you forgot that you didn't have 27 coordinates, you compute it with this general ansatz, you will find it closes up to precisely such terms. So closure of the algebra imposes this this constraint. Okay. Right. Local GL6. Yeah, in the sense, but again, I mean, yes, you can sort of. Again, I mean, I'm not thinking about global obstructions on my internal space and so on, which will general spoil such a symmetry. Okay. The local gauge symmetries of this action are these ones, the generalized diffeomorphisms. That's our gauge structure, and that's like the building, the core of the construction. Okay, and everything will be built such that it's invariant under these generalized diffeomorphisms. And now things become more standard because now, well, I have to implement an infinite dimensional gauge algebra. I have to write invariant terms. I know how to do that with connections, Young-Mills field strength, and so on. And the claim is the moment I do that, this will be exactly 11-dimensional supergravity. Okay, including all the 11 coordinates. And everything boils down to having a solution to this constraint. And now the nice thing is there's a second solution to this constraint. You can dualize either in 11 before you do the reduction, or you first reduce and then you dualize in 5. It's the same. You have a 6 form in 11 dimensions, so that's a dual to the 3 form, yes? Well, again, the 6 form, if you reduce on on 6 dimensions, it will spit out one scalar, which is like the totally internal. Yes, but we have organized the fields according to how they look in that 5+6 split. And so, for example, that 6 form, it will have a totally internal component where all legs are in the 6 internal directions. It will have precisely 1. That you will see among the scalars in this matrix and so on. It will spit out some vectors, which we will see here and so on. And the higher ones, I'll come to that in a second. Some of them we will see, some of them will just not appear in the Lagrangian. But I could go on shell and define them on shell by duality equations if I wish, but I don't have to. It's like in 11 dimensions. In 11 dimensions, I don't write an action which carries the 3 form and the 6 form. The action in 11 dimensions only carries the 3 form. But I can look at the field equation and on shell define a 6 form. And it's the same here. Some of the forms I see in the Lagrangian, others I can only then define from duality relations. Okay, so now the nice thing is this has a second solution. in which you break E6 differently, not to GL6, but to GL5 times SL2. So 27 breaks into 4 pieces, and you only keep this first piece, which is now like 5 directions inside of the 27. But the nice thing is these 5 are not a subset of those 6, because those are kind of complementary decomposition. Okay. And the reason is kind of intuitive. If we restrict coordinate dependence to those 5 coordinates, which are different from those 6, in fact, this very same Lagrangian will describe type 2b supergravity, which is a different theory, which is not the one I get from 11 dimensions by reduction. If instead I would choose 5 derivatives inside of those 6, well, I would get the type 2a theory, which is indeed nothing but a reduction of 11 dimensions. Yes. But you see, I kill all those. I only have fields depending on those first 6 coordinates. And then I'm back to precisely what I started from 11 dimensional supergravity. Well, in some sense, by high dimension, you mean 27. In some sense, that's not really a space. It's think of that as kind of, it's sort of fake. That you would, okay. All this is on the level of the Lagrangian. Depending on how I solve my section constraint, this Lagrangian will actually live in different dimensions. And then, only once I have solved my section constraint, restricted coordinate dependence, only then I should integrate that over my full space-time and get an action. Full means those 5 in which this is a field theory, plus those 6 internal. Or it means those 5 plus those 5 internal. Then I have a 10 form. The Lagrangian is here in this form is always a density. And it's a density, if I, well, depending on how I solve my section constraint. If I do like that. Say again. Oh, sorry. Okay. No, I think I understand your question. Okay, very good. I integrate that over the full 11-dimensional space. However, the density factor I put in, as we discussed a moment ago, is just the determinant of the 5-dimensional metric. Okay, and that is true here and here. So what I change is just the integral in front, but the density, it will always be density with respect to 5-dimensional space. But the statement is the field equations I get from that are precisely the field equations from 11-dimensional supergravity, or are precisely the field equations from type 2b. Say again, in what sense is he? Yes. Oh, yes. Right, but that is because the translation of these fields into the fields of 11-dimensional supergravity is not trivial. So, for example, what I see here as a 5-dimensional metric, that is not just a block of the 11-dimensional metric. It's a block of the 11-dimensional metric multiplied by a certain density factor. Okay, and so if I plug all that back together with a translation into 11-dimensional fields, in terms of 11-dimensional fields, I will see a density factor, an 11-dimensional density factor. Okay, but all that is really hidden in the translation of these objects into the 11-dimensional objects. Anyhow, I think I'll restrict to the first half of my talk, which is very good. Let's. Okay. Very good. There was a question about closure. Okay, the thing closes if you impose the section constraint, but the intriguing thing about this structure is it closes, but it has a non-vanishing Jacobiator. So because the gauge transformations are reducible, there's a non-vanishing Jacobiator which corresponds to a trivial gauge parameter. So there are non-vanishing lambdas here which have trivial action on all the fields. Okay, and it happens that the Jacobiator, in fact, is such a trivial gauge parameter. So there's no contradiction in the fact that this is a symmetry realized on fields. But as an algebra, this is non-associative in the sense that the Jacobi identities do not hold. Okay. And that has some, that's not a problem again for realizing this as a symmetry algebra, but in fact it is a problem for constructing a Young-Mills field strength. Because now, okay, I cut this a bit short, I will have to extend my Maxwell field strength by the standard Young-Mills extension, because there's a non-abelian algebra here. So this bracket just refers to the bracket of such transformations. But if the Jacobi identities do not hold, then this thing itself will not be a covariant tensor, as you know. And one way to correct that is by adding to this field strength yet more forms, two-form fields, which may precisely absorb whatever goes wrong with the transformation of these first two pieces. And so that's what turns out to be the right answer. So the field strength which I'm writing here is in fact the Young-Mills extension of our previous field strength, but it also carries a coupling to what are the 27 two-form fields which we have. And see, they don't come in a completely arbitrary manner. They come under internal derivative and contraction again with this D symbol. But the number of two forms we need in order to correct this field strength is precisely 27. And that's good because remember in 5 dimensions, there are 27 two forms which are dual to the vector. So this object is not, is kind of intuitive and it shows up in this place. The bracket, okay, I'm a bit short. The bracket is basically the bracket which I obtain if I from the algebra here. So I mean, this is a transformation. I can compute the commutator of two such transformations. The algebra closes, so that defines me a bracket on the algebra. Well, it's not scalar field dependent. There are no scalar fields here. It's not constant in the sense that it carries, of course, internal derivatives. You see, I mean, the action of this guy is done by internal derivatives. If I had only standard diffeomorphisms, then this bracket would just be the Lie bracket on the internal space. If I would not have the projection here and just a standard internal space, then this would just be the Lie bracket on the internal space. But now that this is a more complicated structure, well, this also becomes more complicated. Yes, here. A mu is the gauge field for that symmetry. So it's the one form. The mu is the one form index of that field. Okay, it's a gauge field which makes this symmetry local. So covariant derivatives go with this gauge field, go with the action of a gauge transformation whose parameter is the gauge field. Okay, and so another way of defining this field string is you could say I take the commutator of covariant derivatives. Okay, so that is the full F, which shows up in this Young-Mills term. The topological term also blows up now because we are non-abelian, and it's typically ugly to write a non-abelian Chern-Simons term. So the easiest is to write its external derivative as a formal 6 form, and then it just takes this nice form. It's an F wedge F wedge F, but now F would be the full covariant tensor here. And then there's a second term. H would be the field strength of that B. So H is a 3 form, H wedge DH. That's the internal derivative. So from the 5-dimensional point of view, this is like a 6 form. H wedge H. Okay. And so that cures one nice one obstacle you might detect here. I have introduced new fields to my Lagrangian. That looks bad because we don't want to add degrees of freedom, as we discussed before. But the way they come, well, they extend the field strength here, but they also extend the topological term. So in fact, if you compute the field equation, if you vary with respect to B, it's not a Lagrange multiplier. Variation here will just spit out an F, basically. Variation here will just spit out star H. So the field equation of B precisely gives you the duality equation between vectors and those two forms. Equation is very simple. Schematically, it is something like F is star H. A star, 5 dimensions. All my sort of field theory notions refer to 5 dimensions. And there's some matrix which, because they carry different indices, there's a matrix here. Absolutely. That ensures that my B is not independent. So it was not a mistake to introduce it to correct for things, because it kills itself, which is good. Okay, and the last term, let's just very quickly do that. The last term is the one, so far all my modifications came from just sort of covariantizing the objects to make them invariant under generalized diffeomorphisms. And by that I introduced already a number of internal derivatives, and that precisely reproduces the high dimensional couplings. But then there's a bunch of terms which I cannot get that way, and all those I put together to what is called the potential. That carries only terms which are bilinear in internal derivatives. So when you reduce, you don't see this term anymore. Okay, and so that you can entirely express in terms of derivatives of this M matrix. And it turns out this is far from manifestly invariant, because they're like naked derivatives. It's not manifestly invariant under generalized diffeomorphisms. However, if you do the computation, you can show that this is an invariant of generalized diffeomorphisms. And in some sense, you can think of that as like a generalized version of an internal curvature scalar, where this M would play the role of a metric on that internal space. And the form G is that, G is the determinant of that external metric, which, and yeah, sorry, E is the square of G. Yes, I'm sorry, that's a bad notation. Well, it's not bad, but it's not defined. Okay. So in some sense, these couplings, you should compare them to taking the Einstein-Hilbert action and writing it out in explicit derivatives of the metric. And you can write Einstein-Hilbert as sort of bilinear in dg. And then also it looks like something which has no reason to be invariant, but it is, because it comes from a curvature scalar. And so something very similar happens here. Okay, let me start to wrap up. So this is constructed such that every term is invariant under generalized diffeomorphisms. And by generalized diffeomorphisms, we mean internal diffeomorphisms. You can show moreover that if you also want to implement external diffeomorphisms, so 5-dimensional diffeomorphisms, none of these terms is by itself invariant under 5-dimensional diffeomorphisms, which looks strange because it's like a 5-dimensional, it looks like a 5-dimensional field theory, but that is because external 5D diffeomorphisms now can also depend on X and on Y. And of course, those which only depend on X, the action is trivially invariant by that, because that's how it's constructed. But those which depend on Y, in general, will make the different terms talk. This is not, those diffeomorphisms are not at all manifest in none of the terms. And turns out it makes all the terms talk, and it fixes all the relative coefficients. Okay, so if you want to implement also external diffeomorphisms, that fixes all the relative coefficients. And so putting all together, this is the unique two-derivative action which you can write down, which has invariance under internal and external diffeomorphisms. Okay, and again, it's a thing which typically you would get from supersymmetry, but here it's totally determined just by imposing the bosonic symmetries. It's the action. So there was just about time. Or 5 minutes? Very good. Very good. And so the picture is like the following. We can now, that is like the universal Lagrangian. Depending on how we solve that section constraint, we can translate all this into 11-dimensional supergravity or into type 2b supergravity. And the field equations we get from here give us back precisely the ones from 11 dimensions or the ones from type 2b. It's a nice universal form. it was made, of course, after it was constructed or tailored after the form of 5-dimensional supergravity. So remember, I started my discussion here, this compactifying 11-dimensional supergravity on a torus, and that would give me 5-dimensional supergravity if I just throw away all the internal coordinates and I do some work to redualize fields. I could do the same from type 2b on a 5 torus. I throw away all the internal coordinates and I do some work and I got here. Or this is made such that I throw away all the internal derivatives. I do no work because that's how it's done, and I get down here to 5-dimensional supergravity. So in some sense, that is how things come together. There's a nice way of thinking of that, sort of reversing the logic. In some sense, you could think of this high-dimensional, or well, yeah, the high-dimensional Lagrangian. It's kind of deforming maximal supergravity in 5 dimensions by switching on internal derivatives and promoting a particular infinite dimensional gauge algebra on that theory. So if you do it a bit more formal, it would mean you start from 5-dimensional supergravity as you know it, as a 5-dimensional Lagrangian. You promote all your fields by giving them kind of some trivial dependence along that extra internal coordinates. However, you introduce no derivatives along here, so it remains a 5-dimensional Lagrangian, like an infinite copy of 5-dimensional Lagrangians. So you gain a new symmetry, which is like translations in these new internal coordinates, and now you gauge a subgroup of E6, which is a symmetry, together with those translations, and that subgroup will be the generalized diffeomorphisms, and that's the way you can formalize all this, and that's the way to come up basically from 5-dimensional supergravity up to this form of the action, which then translates into 11-dimensional type 2b supergravities. In some sense, it's a way of thinking of these theories as kind of deformations of a lower dimension theory, which is kind of neat. And so mostly people use this framework to do supergravity computations for consistent truncations, Kaluza-Klein spectra, and so on. Because in some sense, I mean, in the most pragmatic way, you could just say, well, these are new variables for supergravity. These are new variables to describe the old theories. And it turns out many of the sort of classic computations of supergravity in these new variables, they become kind of trivial. Whereas in the old variables, they are a nightmare, and nobody could do that until now. But in these new variables, many things simplify a lot, and that's yeah. So what I want to say is about can we do something similar for exotic supergravities? But we had many good discussions, so I'll skip that part. Maybe I just give you 2 slides to finish just give the idea of these are all the standard supergravities which we have embedded and somehow into our construction. The nice thing was these two, which are different in 10-dimensional type 2a and type 2b, different supergravities, still they fall both in this universal Lagrangian, just with different solutions of the section constraint. Okay. Now, if you complete this list, there are a few extra theories in 6 dimensions where you have these exotic multiplets, again, chiral supersymmetry, n equals 3, 1, 4,0. As I said, they don't carry a graviton, they don't carry spin. Well, the spin 2 here is carried by mixed symmetry tensors, and so they're only known as 3 theories. So the idea or the hope is that maybe we can extend all this framework to get a unifying framework by solving yet differently our section constraint. We may also embed those 3 theories that we know we can, but the hope would be that this gives a path even to approach the interacting theories. In the spirit I was just mentioning before, in the spirit that we can think of these high dimensional theories in some formal sense as a deformation of a lower dimensional theory if we identify the right gauge structure. Okay, so I think that's a good point to stop with the. So it's that's a vision. Thanks. The previous? This? That is the 6-dimensional theory. So instead of a graviton, which would be like a 2-index tensor, the 3,1 theory carries like a Cartwright field, and the 4,0 theory carries a 4-index tensor. And they are such that, again, after reduction to 5 dimensions, they all give the same theory. They all give standard gravity on the free level, because all these are only known as 3 theories. In 5 dimensions, they give all 3 supergravity. Okay. And so the question here is, can we sort of by finding a better solution of that, or more subtle solution of the section constraint, can we also, in a framework which looks 5-dimensional with one internal dimension, find theories which in fact describe the dynamics of these fields? Okay, and the answer is, on the level of the free theories, yes, we can. We can do that within this section constraint. We can find directions which precisely reproduce the action of these free tensor fields. The big question is, can that give any hint to approach interactions of these theories? Yeah, I have a lot more to say. Let's discuss that. It turns out you have to twist a little the section constraint. If you just take your naive section constraint, you come back only to the theories you know already. You have to twist it in a slight way, and you see that this twist at the moment makes only sense for a free theory. And it looks like if you want to go to an interacting theory, it should be a twist which brings in the scalar fields, the internal metric. And so it seems to suggest something like, if you want to find interactions that way, you should somehow intertwine space-time with that internal scalar metric. And do that in order to switch on that internal coordinate, which brings you from 5 back to 6. Okay, I have more formulas on that, but I can show you. That's a good question. Typically, in all the cases where we have some kind of high-dimensional standard, high-dimensional interpretation, we should identify some GL groups, and typically there are different GL groups, and they may point to different high-dimensional origins. The question is, so the group with respect to which you decompose, if that would be a different type of group, would that be like a different type of in principle, I mean, the rules are there. You have the theory. You could break your E6 like that. You could simply spell out the terms and see what type of interactions does this resemble. So it should be something then which would not look like diffeomorphisms, but one would have to spell it out. That could be indeed. Yeah, I haven't thought about that.